Hello and welcome to lecture number 11 on the definition of a derivative. All right, so you're going to learn a lot about derivatives in this lecture, but at their core, a derivative is simply a slope. So let's start by reviewing a slope. Recall from high school math that the slope is given by the rise of a function divided by the run of a function. So if we have, for example, this line here, we can calculate the slope by saying, what is the rise over the run? Well, we can look at this figure and we can see that the run in this case is equal to 5. So we go from the point 7.5 to the point 2.5, and we get a rise of f of 7.5 minus f of 2.5. So we take the final value minus the initial value of the y-axis, and that gives us our rise, divided by the final value on the x-axis minus the initial value on the x-axis, and that gives us our run, and we end up with a rise of 10 divided by a run of 5, which is equal to a slope of 2. All right, luckily, this is an equation for a line, which we can also directly interpret as having this as its intercept, which means it has a y-intercept of minus 2.5, and it has a slope of 2. So the equation for a line is the intercept plus the slope times the independent variable. All right, so that's how to find the slope of a line. What about the slope of a quadratic at the point a equals 5? So if this is our variable x, what is the value of the slope at x equals a? Well, in this case, the slope is going to change depending on what that value of a is. If we evaluate the slope over here, it's going to be a negative slope. If we evaluate the slope over here, it's going to be a positive slope. So we can talk about the slope of a quadratic or any curve at a particular point A by asking, what is the slope of the tangent line, the line that comes along and just barely touches the curve at the point A? So this line that I've drawn here is the tangent line to f of x. And then we just calculate the slope of that tangent line at that point x equals a. So we get the same thing. We get final minus initial, the rise over the run. So we have a rise over a run here. And we get the same thing, the slope. All right, so this slope of this tangent line is by definition the derivative of the quadratic at the point x equals a. So the derivative of f of x at a is the slope of the tangent line. It is the slope of the curve at that point a. All right. Formally, the derivative is given by this limit that is motivated by this rise over run. So if we take the rise of a function, the final value, minus the initial value. So if this is our point x, and this is x plus delta x, then we end up with f of x and f of x plus delta x. So our rise is f of x plus delta x minus f of x, and our run is x plus delta x minus x. This cancels with this, and we just simply get a run of delta x. And then we ask, what is that rise over run as the delta x gets smaller and smaller and smaller and smaller and smaller, and the limit as your run goes to 0. So the derivative of the function f of x is equal to the rise over run as the run goes to 0. All right. So note that there are several different ways to represent a derivative. They're all saying the same thing, we just have different ways of using notation. The first way of using the notation is like what I've done here and use fractional notation. So we have d of f of x dx, we write it as a fraction, and the way that we say this in words is like each letter separately. So df dx. Now, note that these d's cannot be canceled. These d's are not separate things. They are one quantity. So you have d over dx is one quantity and is known as an operator. Now, that's a fancy math word to just say that we evaluate the derivative of the function. So sometimes we remind ourselves it's an operator by moving those d's over by themselves. So we have d by dx of the function f of x. We apply this derivative to the function f of x. And then the final and most lazy notation that we have is as a prime notation, where we simply put a prime in there and call this f prime of x, which tells us the same thing. So this is a very shorthand notation for these same things. So remind yourself that you can't cancel the d's, and that's because you could actually write this as operator notation, where you take that d over dx out in front. All right. So now we have the formal definition of the derivative as a slope as the run goes to 0, and we have 3 different ways of representing that derivative. But let's use that definition of the derivative to actually evaluate the slope of a function. So consider this line here. We have f of x is equal to 17x plus 1. This is the intercept. This is the slope. So if we use the formal definition of the derivative, we should get back this slope. So let's try to do that. Well, first we need to plug in f of x plus delta x. This means that everywhere you see an x in your equation, you're going to put an x plus delta x in there. It's very important to use parentheses so that you don't forget what you have to distribute here. And then you have x plus 1. And then you're going to subtract the whole function evaluated at x. So you have 17x plus 1. And then you're going to divide this by delta x and take the limit as delta x goes to 0. All right, so what do we have here? Let's start by simplifying. So we have 17x. Let's distribute 17x plus 17 delta x plus 1. Minus, make sure to distribute your minus sign, 17x minus 1 divided by delta x, and we're taking the limit as delta x goes to 0. All right, let's do some canceling. This minus 17x cancels with that. This plus 1 cancels with this, and we're left with the limit as delta x goes to 0 of 17 delta x divided by delta x. Now, nicely, those delta x's start to cancel, and we end up with 17. All right, so once again, we can apply this formal definition of the derivative to reobtain the slope of a line. Now, that was for a line, but what about for a quadratic? So as we saw on the previous page, if we're trying to take the slope of a line, it's simply the slope here, but when we take the slope of a quadratic, it's going to be the slope of that tangent line. All right, so what happens if we take the derivative of the quadratic x squared and we evaluate this derivative at x equals 3? So once we have taken the derivative, we say, what is the derivative at the point x equals 3, just like we have shown here. Well, that was actually x equals 5, but we're going to do x equals 3. Okay, so let's use our formal definition of the derivative. We have the limit as delta x goes to 0 of df dx is equal to, now we have to do f of x plus delta x minus f of x divided by delta x. And then in our case, this becomes d by dx of x squared is equal to the limit as delta x goes to 0 of x plus delta x squared minus x squared divided by delta x. Expanding, we have the limit as delta x goes to 0 of x squared plus 2 delta x times x plus delta x squared minus x squared divided by delta x. Now, let's do a bunch of canceling. That x squared is going to cancel with that. Now we have a delta x in the numerator and the denominator, so we can cancel one of those delta x's, and we end up with the limit as delta x goes to 0 of 2x plus delta x. Now, remember that sometimes the easiest way to evaluate a limit is to simply plug in the value. If we plug in 0, this goes to 0, and we simply have 2x. Now, there's one more thing we have to do here. We have to evaluate this at x equals 3. So we're going to plug in x equals 3 here, x equals 3, which means we're going to plug in x equals 3 there, and we're going to get 6. Okay, so that gives us the derivative of the quadratic x squared evaluated at the point x equals 3. All right, so now that we have the derivative of the tangent line at the point x equals 3, can we get the equation of the whole tangent line? So recall that the equation for a line has this form that we have the dependent variable, which in this case is our tangent line, is equal to the slope of the tangent line, which is simply the derivative, d by dx, of f of x, evaluated at x equals 3, times the independent variable, which in our case is x, plus the intercept. All right, so this intercept is a little bit challenging, and we'll just leave it for a couple seconds from now, where we'll talk about how to actually calculate this intercept. But the first challenge is to calculate the slope, which we actually did on the previous page, because we evaluated the slope of the tangent line, which was the derivative, at x equals 3. So we had d by dx of x squared evaluated at x equals 3, which was simply 6. So we already found the slope. Now, how do we find that intercept? Well, the easiest way to find the intercept is to think about what we're trying to do here. So we're trying to find the intercept of this tangent line to this curve. Now, what does that mean? Well, it means that we take the value of the function at a, that's that point there, and we know the slope of this, and we want to say, okay, what if I take that slope and I travel backwards minus a units? So I take the value of my function and I travel backwards, hence a minus sign, a units at a slope of df of x dx evaluated at x equals a, and that will give me the intercept down here where my tangent line eventually comes and hits that y-axis. So here we have our intercept plus our slope times that independent variable x is going to give us our tangent line t of x. Okay, so let's try this out and evaluate the tangent line here. Well, what's the value of our function x squared at the point a equals 3? That is simply 3 squared minus 3 times our derivative evaluated at a, which we had up above, which was 6. So we have 9 minus 3 times 6, which is 18, which gives us an intercept of minus 9, which means that our tangent line ends up having an intercept of minus 9 plus a slope of 6 times our independent variable. And this is the tangent line to the quadratic function x squared at the point x equals 3. All right, so what we've done so far is we've talked about the meaning of derivative as a slope. We've used that slope definition as a rise over run to take the limit as the run gets smaller, smaller, smaller to get the derivative of a function at a particular point. We use that formal definition of a derivative to evaluate the derivative of some functions, for example, a quadratic. And then once we know that slope of that tangent line, we can actually find the equation for the whole tangent line by using that slope and then using that slope to calculate the intercept and to get the tangent line. All right, so we've focused on, so far, the meaning of the derivative as a slope. So we have a rise over a run. In other words, we have dy dx, which is the change in y divided by the change in x, which is the run, which we could say in words as the slope of the function y with respect to variable x, where these are our numerator and that is our denominator. Another way of interpreting the derivative is as a rate. So what if instead of x and y here, we have time and distance? I'll use a capital D. Time and distance. Well, then our derivative, which is dt, is like the change in distance divided by the change in time, which is a distance per unit time, which is equal to a rate. So a derivative can be interpreted as a slope, or it can be interpreted as a rate, depending on what kind of independent and dependent variables that you have. All right, so a way to say this in words is that we have the rate of change of d in time t, where d and t are dependent and independent variables. All right, so with that interpretation, please use that to complete the self-study question, and I'll see you in class.